Right, let's get these volumes right because I've got a bit of an echo. A bit better. Can you hear me okay? Got a new mic today, so hopefully this is better than the headset. A lot clearer and allows me to have my fan on, keep me cool at the same time. Cool. Right, so let's start by talking about what this is going to be. Obviously, the aim in the end is to write game, 16 kilobyte game. The current vote is for, let me remember, single screen arcade, clear all the enemies and get to the exit. But before we get to that, I'm going to talk a little bit about assembly, why we use it, what it is, just because I want these videos to be a source of kind of education for people and for people to be able to share their ideas and suggestions as well as we go along. Hey Cola, play Minecraft, lovely. Okay, so today I wrote the starting soon demo that you saw at the beginning. I'll quickly switch back to it just to show you. The mic will go off while I do this, but oh, thanks for the host, Cola. It's really hard to see my alerts actually. I probably need to find a better way to do that. Okay, but I'll work that out later. So yeah, I wrote that demo today because I thought it'd be a good idea to start to teach you how to write something like that quickly and easily. Obviously, we're not going to jump straight into that, but that's what we're going to try and aim for in this session. I don't know how many of you have got Kickassembler set up. I'm going to assume you have the ability to load an ASM file and compile it. If anybody doesn't have that, if you let me know now in the chat, I can quickly go through setting that up. Thanks for the host as well, Dom. Okay, I'm going to assume you all know how to do that. So before we get into a full program, I want to talk a bit about the memory and how the 6510 chip reads the memory. So the 6510 is an 8-bit chip, which means it can see numbers from 0 to 255. It reads them as binary, obviously, like all CPUs. And we represent binary in Kickassembler using the percent symbol. And then we can put 8 bits into it. So how many is that? That's 8, so that's 255. We can also represent that as a decimal number without the percentage sign, or we can represent it as a hexadecimal number. So all numbers in 6510. Zoom in on my editor a bit. Okay, let me try making my text a little bit bigger. There we go. Oh, chunky text. Is that better? How's that? Cool, okay. So that's 3 ways for us to represent the number 255. Mostly I tend to use the hexadecimal numbers, but occasionally it's more convenient to use the other 2 for various reasons, and we'll get into them shortly. So, what is machine code and assembly language? So, computers run on machine code, which, if I can show you, there we go. So this is a Kickassembler machine code program. Obviously it's not very readable, and this is why we have assembly language. But this is fully runnable, so just by using the byte command we're able to write a program that will run in memory. So what this does is it writes a basic program with 10 SYS 2059 and then runs some machine code which is at the address 2059. So let's just press F7, I should be able to run that. It's a very simple program, just sets the border to black and then exits. But obviously that's not very readable, so what we do is we use assembler. and Kickassembler allows us to do lots of nice little things. In fact, before we go into the next step, I want to just explain this line here. So star in Kickassembler is the current address of where you are in the program. So this is saying set the current address to 0801. Now there's a reason why we picked 0801, because it's the beginning of BASIC. We need to have a program at the beginning of BASIC, otherwise we have nothing to run. So let me show you the memory map. If you haven't got this memory map, I definitely recommend getting a memory map or use this one. I'll try and make the text a bit bigger on that. So this site lists all the memory addresses and what they do, and if we scroll down, in fact if I just do a search 01, you can see this is the beginning of BASIC. And so what this is doing is it's writing a small BASIC program. It's these bytes here and then some machine code. Now to make that more readable, we can use assembly language, and that looks like this. So there's only two things inherently Kickassembler about this. One is the label, although you'll probably find most assemblers handle the labels in the same way. Can we chart again? There you go. And the other one is this basic upstart 2. So what is this doing? So this is basic upstart 2 is a small command in Kickassembler that generates the basic program for you. And you write basic upstart 2, and then in brackets you write the name of a label where you want it to jump to. And this is the equivalent of going into basic and typing 10 sys and then the address of wherever it is. The address here is this, and this is the label here. And this takes care of putting it at 0801 and working out where the entry address is here. So let's run that program. We can see it will do exactly the same thing. Okay. So that's why we use assembly language, because machine code is just impossible for a human to understand. Although back in the day, a lot of people, a lot of children, myself included, would learn assembly language by reading up the opcodes and writing, handwriting these bytes like this and poking them in through BASIC. Obviously, we don't need to do that nowadays. We've got modern IDEs like Sublime and assemblers like Kickassembler, which make it a much easier task. And even back then, you had assemblers like Dr. Watson. You were taught to do it like that with opcodes as well. Yeah, it's how I started doing it. I started doing it by writing my programs out like this, and then working out how to convert it into this. And there are ways to do that. There is another great site which I'll show you now, actually. It's this one. I'm not sure if you can see that. I will put these links into chat actually, and then you can use these. So this is the opcode one, and this is the memory map one. And so we can see, if we look at the machine code here, A9, so we go down to A9, that's load accumulator. I'll explain what these mean soon. 0, and that's a store accumulator, and that's an RTS. So let's go back to this. Let's run this program. And if you bring up the monitor, if you don't know how to do that, it's Alt-M in Vice. We can see the memory, and we can see the disassembly for this piece of code. If we scroll all the way down to, I actually can't zoom in on that, that's quite annoying. Okay, let me... And there we go, we can see our program there, and it's the same as we've got in here. Now, before we go any further, I want to introduce you guys to C64 Debugger. Put the link for that in the chat now as well. If you haven't already used this or got this set up, I definitely recommend it. If anybody wants any help getting this set up in Sublime, please again just send me a private message or ask me in the Discord. Links at the bottom of the screen, and I'll gladly help someone set that up. But basically you can set it up so when you compile, so instead of using F7 to compile, you can use Shift F7 and it will compile in the debugger and run in the debugger. Now the debugger is great because this allows you to see everything that's going on and as it happens live. Now the reason this is going crazy here is because it's actually running the kernel, which is flashing the cursor here. Although it looks slightly buggy in the debugger, it's too ready. Oh no, that's probably right actually. Okay, so I usually go to Control F8. I find this view easier to use for myself. And you get a memory view here. And you get the code that's running here. So if I just zoom up in the code, if I press Control G, no, not Control there, Control G in here, type in 0801, you can see there is our code. And it's the same code we can see in our IDE here. So what is this code? Alright, so I've shown you how to start a program, but I've not explained anything what's going on. So let's talk a bit about what actually happens on the processor. So this is where the debugger is very helpful. So the processor has a number of registers. It has 3 number registers. It has a stack pointer, a program counter, and a processor status. And they're represented at the top here. I don't know if you can see my cursor. You can actually. Oh yeah, it's very, very small. So at the top we've got PC, which is program counter. That tells us where the 6510 is actually running programs from currently. That's a kernel routine at the moment. It's probably responsible for flashing this cursor here. There's the accumulator register, the X register, and the Y register. They're number registers, and I'll explain what they do shortly. There's the stack pointer, which you don't need to worry about for now. We will get into that at some point. And then there's the processor status flags. And again, I'll go through what these do very shortly. But now let's concentrate on the accumulator. So the accumulator is, you can think of it as a variable if you like. It's an area of memory. I don't actually know where it belongs. I think it's just on the processor. I don't think it has a memory address. But you can store any number from 0 to 255 in there. And you can define that however you want. And the way we do that is we use this command, load accumulator. Now, commands consist of an opcode, which is the 3 letters that make up the command, and an operand, which is the numbers that go after. Now there can be 0, 1 or 2 operands. The load accumulator always takes 1 or 2. I will explain how we do that. So to put a number into the accumulator, we use what's called immediate mode. Immediate mode, you put a hash symbol. That just means take whatever number's next and put it in the accumulator. So I'll do that with 0, and that loads that into it. If I go into the debugger and put a breakpoint in there. So what's cool about this debugger is you can click on any address in the side here, like that, and when I reload the program, reload. Why is it not reloading? It's broke somewhere else. Let me check the breakpoints. Yeah. Oh, there we go. And you can look, if you press F9 while you're in the debugger, you can bring up this menu. Allows you to load. It's very, very similar to Vice. For some reason it's not breaking on this point. That's fine. What I can do is I can tell it to continue. And instead I can type the command in. So we had 2062. And you can see the address here, there that I'd marked as red has now gone pink, and that tells us that the processor has got to that point and has now stopped. This command hasn't been run yet, it's about to be run, it's the next thing to be run. You can see up here the accumulator. So if I set the accumulator to 8 and then I press F11, no, Control F10, sorry, it will go one command ahead. You can see how this grey line has moved on to the next line. So it's now run this command, and you can see the accumulator at the top has gone to 0. If I let that continue, and you can see now, why has it put that value in there? Oh, it has run that command. Okay, so let me go back to what I was saying. So if I run that command again, SOS 2062, my bad, I misunderstood what it's doing. So when it goes pink, this command is the one that has just been run. So any number I put in here is the number that's going to be stored in this next address. Oh wow. Hi Hayes, that's a big raid. Hi guys. How was the multiplayer tonight? Was it good? Who won? I'm going to have some wine for a minute. It does make the border black. We're starting with the basics, the very, very basics. So I want people to understand how the debugger works, and I'm failing to understand how it works myself already. So, well, that wine's very nice. So yeah, as I was saying, when the debugger reaches a breakpoint, the line that it's on will go pink, and we will see the results of the instruction that's just been run in here. I've just changed the value to 9 instead of 0, and so when I continue, it goes brown instead. So what is this second command? This is a store command. This allows us to take the value that we've stored in the accumulator and put it into an address. Now, when you first get into Commodore 64, you're probably going to be confused by all these addresses. I think the... No, this isn't the making of the Airwolf 3 stream. This is the making of an arcade game. Yeah, so as I was saying, when you start Commodore 64 programming, I doubt you're going to remember every single memory address, and even to this day I still refer to this memory map constantly. There's certain addresses that you will remember, but there's others that you'll probably have to reference quite a lot. Later on I'll show you how to make labels to simplify kind of remembering all of these. So what we're interested in is the border color, and you can see D020 and D021 are the border and the background color. You will probably have seen them in BASIC as something like this. To set the border and the border and background to black. And that's all we're doing here. These basic commands essentially do this when they run. They take a value and they store it in that address. So you can think of a load accumulator and a store accumulator as a poke, basically. So let's add another line, and that will now change the background to black as well. So if we run that, and we see the background's black as well. This is called absolute mode. Sorry, not that. This is called absolute mode. This is used by many opcodes, but the store accumulator and the store commands are the ones you'll probably use it the most. We can change these numbers to the values that we're used to in BASIC if you want. Personally, I prefer the hexadecimal numbers, and I'll show you why in a second. And it will do the same thing. And if you're really insane, you could do it in binary. Let's see, can I work out the binary for this? It would be 1101. I'm guessing here, so this could crash. I think this is right. Yeah, cool. Okay, so the reason why that works is because we're just passing a number in. If we did that, it would become immediate mode, and actually there is no store immediate mode. It just doesn't make sense. You can't store a number in itself. You have to store it in a memory address. So the store commands are for memory addresses. Let's put this back to the mode I'm familiar in. Now, the reason why I like to use hexadecimal is, I will show you in the debugger. Is when we look at the code, let's go to, let's go into that mode. I don't know if you can see that. Can you guys? Can you guys see the memory there, or is it too small? I imagine it's quite small. Let me see if I can make it any bigger. Okay. About as big as it's going to go. Okay, so you can see the store commands here, and you'll see that with the load command, we've got 2 bytes that make up the load command, and we've got 3 bytes that make up the store commands, and 1 byte that makes up the RTS command. Now the reason for that is because with the load command, this is an 8-bit number, and there's these 16-bit addresses. So in order to use a 16-bit address, we put 2 8-bit numbers in. And here's the fun part. They're stored in little endian format, if you guys know what that is. Basically what it means is, in memory, this address here looks like this in memory. The little part goes first, and then the big part. It's called little endian format, and it's kind of, I'm not sure how many processors do that nowadays, but it's certainly kind of an old styly way of doing things. This is why I like to use hexadecimal, because that is how it's set out. You've got 1 operand, 2 bytes, 1 operand, 2 bytes, 1 operand, 1 byte. So it's much easier, I think, personally, to use hexadecimal. Yes, it doesn't make sense, does it? It's called, I always get confused with it, but it is called little endian. It's very, very annoying. Okay, let me read some of the chats if I've missed anything. Okay, how do you make Sublime compile and then launch Vice? Okay, so if you follow the Sublime install, Sublime Kickassembler, let me find the package. I do apologise if my keyboard is clicky. I've got my microphone sat right next to it. I tried to put a noise gate on, but it kept cutting my voice out as well. Yeah, so I'll put this link into chat. So this link will let you install the Kickassembler package for Sublime. It has instructions for Mac OS X and for Windows. I use both. I use Windows at home, I use Mac at work. So I try to use stuff that will work for both, with the exception of some rather annoying things like Charpad and SpritePad. They don't work on Mac OS X. You have an Apple II next to you, but this is a 2009. An Apple II is great because that's also 6502. So the stuff you learn here you can use on the Apple Mac, on the Apple II as well. Although the memory addresses will be completely different. Okay, so where are we? Okay, so we've learned what load accumulator does, and we've learned what store accumulator does. So let's do something slightly different. Hi Chiswicked. Who won, by the way, tonight? Were you playing California games? That's what I saw on the Twitch banner. Yeah. Actually, an interesting thing, the 6502 is, in my opinion, one of the best CPUs ever. It's so simple to understand, and it's so good that even the Terminator used it, and I'm going to prove that right now. So this is a screenshot from the Terminator, the movie. And I don't know if you can see that. But his targeting system is written in 6502. So there you go. Now unfortunately the 6502 cannot do multiplication, it cannot do division. So if you want to confuse the Terminator, just give him a long division problem. And that's how you'll get away. But yeah, it's used everywhere. It's used on, let's see, 8-bits. You've got the Ataris, you've got the BBC, you've got the Apple. You've even got the PC Engine, which uses an 8-bit variant of the 6502. Why do I say 6502 when I see 64? Okay, so 6502 is the base CPU. It's the first one that used this this assembly language, this machine code. 6510 is a special version of it that they wrote for that they made for the Commodore 64 that has some I/O pins on it that the 6502 doesn't have. There's also the 8500, which is the C64 C version of the 6510, which is I believe it's a low power version of it. But essentially it's the same. And there's the 65C02, which is in the PC Engine, and I'm sure there's more as well, but I can't remember them all offhand. I think my issue was I used Homebrew to install Vice. You need to make a link in applications to get it to work. Yeah, so on the Mac what I found was if I had it in applications, in fact I'll show you now the preferences file. So once you've got Sublime installed and Kickassembler installed, if you go to package settings, you've got this Sublime Kickassembler preferences. Whoa, wow, that's big. Let me turn word wrap on. And so this file tells Sublime where all the files are that it needs, and you can change the paths in here. So if you need to get it to run x64, which is the device runtime, device exe or device application on OS X, you can just change these paths in here. You have to do it on this side though. This is kind of read only. You have to make a copy and use this side instead. And this is how I get the debugger to run. So you'll see over here, I've got debugger here. And the way I've got it to work on the PC is I've got a folder. Let's see if I can find the folder. I've got a folder called C64, a folder called tools in that, and I put Kickassembler and Vice in there, and then I add that to my path environment variable, and then I can just use that instead of the full path. But that by changing Kickass debug path, that allows me to do the Shift F7 to run the debugger. Although I wish it would remember the size of the window. It's very, very, very frustrating. But yeah, if anybody does need any help getting that running, please just ask me, and I'll ask me in either DM or in Discord, and I'll be glad to help you. I've had it running on OS X, and I've had it running on Windows, and I'm pretty sure it'd be quite simple to get it running on Linux as well. I haven't tried that yet. Okay, so we know how to load a number into the accumulator. We know how to store a number into the accumulator. So what is the accumulator, and what are the X and Y registers? So there's 3 registers. We've got the accumulator. Let's do some load numbers in, which can take a number from 0 to 255. We've got the X register, which can also take a number from 0 to 255. And we've got the Y register, which can also take a number from 0 to 255. The difference between the 3 is that X and Y are just what are known as index registers. All you can really do with them is put numbers into them, store the numbers from them elsewhere, and increment them or decrement them by 1. So there's this command, and there's this command. INX increases the value in X, and DEX decreases the value of X. And there's the same commands for Y. What happens when those numbers get to 255? Well, they just wrap round. They go back down round to 0. And likewise, if they're at 0 and they go down, so let's put here, so Y is 0, and when they go back, Y is 255. And that's the same for the accumulator as well. However, with the accumulator, we don't have increment commands, and that's because the accumulator is a little bit special. So the accumulator, you can add and subtract numbers to it. And those numbers can be anything from 0 to 255. So we'll go through those in a bit more detail later on. But for now, all you need to know is that we've got 3 number registers. X and Y are quite simple and just have these increment commands. And the accumulator is a bit more complicated, and you can do more stuff with it. You can also do logical operations on it. I'll show you how to do that as well soon. Actually, let's have a look. Let's get rid of this line, and let's show you the an X register doing its stuff. So if we do that, and we do that, and we do that, and that, who can guess what colour the background will be when I run this program? The border is going to be black because of our first 2 lines here. But what colour do you think the background is going to be? I'm going to take a sip of wine while you figure that out. Ooh, Andy, careful now, careful now. I point you to my parasol stars, by the way. That does not look brown. I think that looks one of the most colourful things on the Commodore. It's on there. So we've got 1 for red, 1 for white. Yeah, I think we all like the brownness of the Commodore, but it doesn't have to be brown. If you do it right, you can make it look colourful. So we've got 2 for red, 1 for white. Okay, let's load up the debugger and have a look. So Shift F7. And it goes red. So now let's explain why. So to do that, I'm going to stop the program there. If you press into this window, I'm going to do it on Control F8. So if I go to Control F8, I've got the same window down here. Let's make it a bit bigger. So when you're in this view here, although annoyingly it keeps putting breakpoints on. I think if you click on the addresses down the side, you get breakpoints. If you click anywhere here, you don't. So if you click in here and press Control G, you can then type an address in, and it will take you to that. It's a nice shortcut instead of scrolling up and down the list. So So let's go down to the program and let's put a breakpoint in here. And now let's run the program. So if we press F11, we start again, and we type the command in to run the program again. And we can see the breakpoint is hit. And if we look up at the, now for some reason the X register says 2. I think there's some bugs actually in this. Let's see what happens when we advance. So it's saying up at the top that the X register is 2, but it should be 1. So, okay, so contrary to what I said before, which was a correction of what I thought was going on, what I originally said is correct. When the breakpoint hits, the command hasn't been run yet. It's the command that's about to be run that you're breaking on. And now I've skipped over it by pressing Control F10, which just moves the program counter on one step to the next command. The load X with 1 has been run, and we can see at the top that the X register is 1. So now if we skip over the next command, which is an increase, you can see that the INX increased the X register, has indeed increased the X register to 2. And F10 again, Control F10, increases it to 3. And now the next command is a decrease, so this will bring it down to 2. And then the next command stores that value at D021, which when we look at our memory map is the background color. Obviously we don't see anything because the background's already red. If I was to make it black and then run the program again, wow, how many? Actually crashed the program. Oh no, it's broke. That's because the breakpoint. Okay, on the breakpoint, so we skip through the breakpoints, increase, 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 and this one will set the background red. And we don't see it. I'll explain why we don't see it straight away in a minute. But for now, believe me when I say it's gone red. In fact, if you go to Control F5, no, which one is it? Control Shift F5, we can see in the Vic view down here, which is the bottom one here, that it is indeed red. I'll explain why we don't see it at the top later on. It's to do with raster timings and where the update is. It's more of a complex topic that we'll talk about later. Okay, so that's increasing and decreasing the X register and Y register. Now, the reason I wanted to talk about machine code before and explain why the bytes are the way they are, is because I wanted you to be able to understand that machine code is that you're poking one into the background color. Okay, yep. The great thing with machine code is it's self-modifiable. So because we know that this command here is simply, let me remind myself, that in memory, we can change this value and we can change this value without changing the code directly. So without writing anything here, I can just increment a value. So the inc command lets you increase a value in memory. So rather than a register, so rather than A, rather than X, rather than Y, this lets us increase a value in memory. So what we're going to do is we're going to tell it to increase this value. Now, this is where Kickassembler comes in handy. So we could type the address in. I know that the starting address is this, but this is going to get complicated. So instead what we're going to do is we're going to give it this label here. Now, this byte is going to be a little bit further on than this label, so we need to know how far. So this is an address, so this is 2 bytes, and this is an operand, so this is 1 byte. So I don't know what the bytes are, but let's just say, so we've got 3 bytes there. And then we've got this byte, which is the LDA, and then we've got the 0 here. So this is entry. This is entry plus 1. This is entry plus 2. This is entry plus 3. This is entry plus 4. If I put plus 4 in there and I run this, what do you think is going to happen this time? What colour will the border go? And again, this is an opportunity for me to drink wine. I like asking questions. I get to drink wine, which I need to top up. Okay, we've got Acmefin saying all 16 one at a time. That would be nice. Cyan from Dom, 2 whites, though it will appear as stripes. Okay, well let's run this in the debugger and have a look. So again, Shift F7. And it's gone white. So points to Hamrath and points to Andy McKnight for Andy Magic Knight. Andy McKnight. Andy Magic Knight. So let's have a little why that did that. So again, if we go to Control F8, because it's just an easier view, I think, to look at memory and stuff. In the F8 view, you can actually see the bytes that make up the command at the side here. So if we click in here, Control G to go to the beginning, we'll have a look at the code. So the first thing we can see is that this inc command doesn't have the label entry next to it, and that's because the compiler, the Kickassembler, gets rid of labels. It actually does store labels in a file somewhere, so you can see them in some debuggers. You can see, for instance, you can see it in... oh no, you can't actually. Oh, you should be able to see it. In one of the views you can see the labels, but internally what it does is it converts this into the address that it needs. So it takes the address of entry and it adds 4 to it. Now you can do maths in Kickassembler, so you could do, you could do anything like that, and you can mix and match number types as well if you really wanted to, and that's really useful because that means you don't have to think. Very good. Jump to the gun. We'll go into the jump in a minute, because this is why I'm showing the inc command, because I'm going to show how to do exactly what Acmefin said. He really did jump the gun, because that's exactly where we're going. Yeah, so you can use these things to really, you can use maths along with the values to really help you, and it doesn't have to be in this absolute mode as well. So this is an address. Because it doesn't have this hash in front of it. If it has a hash, it's an immediate mode. But you can do the same in here as well. So if I did that, for instance, then the number 8 would be stored as the border color, which I think is orange, I think. So if we look at the debugger, what it's actually doing, I've got 3 debuggers open. I should probably close some of these. You've read the script. There is no script. I'm winging this. I'm really winging this. This is a little bit crazy for me, especially as soon as I'm drinking wine. I'm also halfway down my bottle already. I've got another bottle in the fridge, so. But I do like to drink while I code. So if we look here, that inc command has been converted into an actual address, and the address is 0812. And again, like I said, it's little endian, so you can see here the 12 goes first, the 08 goes second. And if we look where that is, on the next line, 0811 starts with A9 and the second value is 01. And that's the thing, so you can see it's already changed it, because this program has run, it's already changed it to 1. So let me restart the program with that breakpoint there. Actually, I'm gonna have to change one of these values. So let me change this value. So A901. So let me change that back to 0. Oh, what have I done? Oh. Okay, unfortunately doing that has kind of broken the view of the debugger, but believe me when I say that this line... Oh, there we go, it's working. apparently just need to move. So you can see the original command that we had, the LDA01, as we wrote in the code, LDA0, sorry, that we wrote in the code. And this increment command is about to be run, and what that's going to do is it's going to increase the value in 0812, which is this value here, this 0, by 1. Control F10, and there you go, it's done it. So now when it runs the next line, it's now loading the accumulator with 1 instead of 0, and that's really useful. This allows you to do things to really speed stuff up. Did single screen arcade win the vote? It did win the vote, and actually in the second vote was for whether we did clear the objects, clear the enemies, or get to the exit, and it was a dead heat between get to the exit and clear the enemies, which suits me fine. So what we're probably going to do is a game where you have a single screen, you have to clear all the enemies on that screen, and the last enemy that you kill drops a key, which you then use to open the door. And whether or not that door is easy to get to is another thing. But yeah, sounds good. Yes, indeed, Mike. Self-modifying code is incredibly powerful. It's probably the first thing you should learn to do if you're trying to optimize your code to get a lot of speed out of it. The first thing you do is self-modifying. The next thing you do is learn to unroll loops. We won't do much loop unrolling, but I will touch on it at some point because it's a nice feature of Kickassembler. But yes, self-modifying code is very useful, but it's handy to understand how that is stored in memory. So when you look at STA D020, what do you think happens if I change this? That. So if I change the command to that, let me just make sure in my head that that's right. 1, 2, 3. Yeah. What do you think that is going to do now? So we're no longer changing this, which was 4, entry plus 4. We're now changing entry plus 6. So we've gone 2 bytes into this. So it's not the first byte, which is the operand, but it's the second byte, which is the first byte of this pair. Remember what I said about little endian? Well, let's try it out and see what happens. I'll run that in Vice. And you see this time the background's gone black. Yeah, exactly right. And that's because we've increased this value here. Remember, again, in memory, this looks like, I can't remember, store accumulator, I think it's that or something like that. So in fact, let me have a look. It is AD, not ED. Okay. In memory, that command looks like that. So by incrementing plus 6, which is 0, so this is, oops, this command has the entry plus 0, entry plus 1, entry plus 2. This command is entry plus 3, entry plus 4, and this command as, let's do it down here, entry plus 5, entry plus 6, and entry plus 7. So plus 6 is this 2, 0. So this command here changes the 2, 0 to a 2, 1, and that changes the border. Anyway, let's try something else. This is the jump command. So this is one of a few commands that can redirect the flow of execution. This is a simple one. This basically jumps, as Akmafin said before. Just make an EA game and fill the memory with A. Do you know what though, Akmafin? A shitload of NOPs in memory would probably be better than most EA games anyway. So, so that's kind of cool. Yeah, so this is the command that Akmafin thought was in there before. He thought he'd seen but hadn't, and that's the jump command. This basically moves the program counter. If we look at here, this is the program counter. It's basically the address of the next command to be run. So we can see here 0813 is the next command to be run, 0813, and it changes it to the address that you give it. So in this case, what it's going to do is going to increment the value in D020, and then it's going to jump to this label, and this label means it's going to go back to here. I cannot for the life of me see what that was. Ah, there we go. Captain John Archer, thank you for the follow. Nice Enterprise reference there as well. Very good. I am going to have to speak with somebody at some point about how you guys see your alerts, because I'm looking at my stream window and it's incredibly small. Can you modify what is in memory without putting in the accumulator? So the increment command will allow you to do that, which is what we're doing here. So what this program is going to do, it's going to increment the border color, and then it's going to jump back to the beginning and resize your alerts to be larger. Is it because I've got them small in my window? I don't even know where I put them in my window. Oh, they're down here, aren't they? Yeah. I thought there'd be some kind of event thing in the... Oh, actually I have got events in here. That's probably easier to look at. Thank you for the follow, Aquafin. Yeah, okay, so go back to what we were saying. So the increment command, as we know, increments a value in memory by 1. And the jump command will change the program counter to point to the new address, and we're passing the address of entry. So what this is basically, well, what do you think this is going to do? Acmafin, don't say anything. Acmafin already knows what this is going to do. Who else knows what this is going to do? Make you have a fit. Yes, possibly. I said don't say anything. I knew you knew the answer. Yes, basically epilepsy border. This also means we don't need this RTS command. I'll explain what the RTS command is in a second. But for now, let's just trust me when I say we don't need it, and that's because it would never be reached. Anything I write here is any code I write here. I don't know why I'd write that, but anything I write here is never going to be reached. So if I try to change the background color to red, that's never going to happen, because the program is going to get to this jump command and it's going to go back to here, and it's just going to keep doing that over and over again. And that looks like this, which won't run because I've still got Vice open. Which anybody who's ever loaded anything from tape will recognize. But as you see, this code never gets run. So what do you think this command is? Knowing what we know about the INC command, what do you think the DEC command is going to do? Will this look any different? Or is it going to look the same? I'm going to top up on wine. Yeah, it will pretty much look the same. I mean, if we were to examine this in detail, we would see that the colours would go, the order of the colours would be backwards, but I mean, to the basic eye is going to look exactly the same. It's the colours changing very, very quickly. So let's explain a little bit about the RTS command. So what does the RTS command do? The RTS command exits execution and returns to the previous subroutine. So what do I mean by that? So we have a concept of the stack. Anybody who's used trying to think of other languages that use stacks, but there's a stack is basically, you can think of it as a pile of numbers. When you put a number on, you can only take from the stack. So you imagine a pile of plates with numbers written on them. As you put things on the stack, you write a number on the plate, you put it on the top of the stack. That's called pushing to the stack. The opposite is called pulling from the stack. If we were to pull a number from the stack, we take the plate off the top, we read the number, we discard the plate. This is the stack. There's two commands for that. There's push the accumulator to the stack and pull the accumulator from the stack. I will go into more detail about those later on. You don't need to use them, but what I will explain is when a program is run, the current address is pushed onto the stack, and when the RTS command is called, the current address is pulled from the stack, and basically a jump happens and it jumps back. We can demonstrate this by doing the following. So if we create a new label here, call it ink border. We can now jump to a subroutine. Anybody who's used any language with functions in, which is pretty much every language out there, even basic, you have go sub and return. This is basically that. This is jump to the subroutine with this name, with this label. Internally, the assembler will turn that into an address, which is this address, and jump to there and wait for a return. And this is what RTS does. RTS will bring it back to here again, to the next line. So this is a function call. You can think of this as a method call. Is there a difference between push and pop, or is it just a different naming convention? Actually, pop is more like pull. Oh, you did say pull. Okay, yes. Yeah, so you can think of a stack like an array using push and pop, or push and... It is pop, isn't it, in arrays in JavaScript and C and things like that. Yeah, it's basically, think of the stack as an array of 8-bit numbers that you can push onto and pull from, and that's the same as push and pop. In fact, I think in some assembly it uses push and pop rather than push and pull. Don't quote me on that though. I can't remember offhand. It's been a long time since I did any assembly, never mind 6510. So what this does, it jumps to ink border, which will increment the border, and then return, which doesn't exit the program, because now we've got this new address on the stack. When we jump to here, what the 6510 does is it says, okay, get the address where I am of the next line. So let's say this is the next line. Get the address of the next line, so this one here, and push it onto the stack, and then jump to this address. And then when it gets to this address, it's 86 is pop. Yeah, I thought I'd seen it in other languages as well, but yeah, it's essentially the same. Yeah, yeah, pull and pop are the same, and push is the same. Yeah, so sorry, to go back to this again. Jump subroutine to increment to ink border. What this will do, the 6510 will take the current program counter address, which is this line here, because this has been executed. So it takes this position here, pushes it to the stack. So the stack now contains. Let me make a little example down here. So let's say this is 0810. Yep. So the stack gets the number 10 pushed onto it and 08 pushed onto it. It then jumps to here. This increments the border color, and RTS happens. When the RTS happens, what it does is it looks at the stack and it pulls these values off. And so it goes, okay, I pull these values back. Pulled off, that's a terribly rude word. And I'm now going to jump to those. And that's essentially what RTS is doing. It's saying jump to the value that's at the top of the stack. So you can think of jump to subroutine as a jump that is waiting for an RTS. So this is a jump, but store program counter on stack, and this is the program counter that gets put on the stack. And RTS is a jump to program counter from stack. If that makes sense. Yeah, so exactly. Jump never returns. Jump will just change the program counter. You can think of a jump to subroutine as a jump, but it pushes the program counter onto the stack. If you just kept using jump to subroutine instead of jump, you get a stack overflow. So to go back to the memory map, where is the memory map? I've lost the memory map now. Okay, never mind. I know how to search for it. 664 memmap. This is literally how I found all the information out. When I came back to the scene 2 or 3 years ago, I just typed things into Google. Where is the stack? It's 100, I think. Yeah, that's right, and it actually pushes -1, but I think it's kind of, yeah, as Akmafin says, it's kind of minor details. It's I think rather than confuse people as to how the CPU works, I think it's easier just to imagine it going to the same. In fact, we'll have a look in the debugger, because the debugger actually stores a stack pointer as well. There we go, processor stack. So you can see here the processor stack is used by BASIC for storing data related to 4 and GoSub. It's also used by machine language for jump to subroutine, and for anything you want to use it for as well. It's quite handy for other things, as I'll show you later on when we get into more advanced topics. But you can see it's only got 256 bytes. So if you do this 128 times, then you've basically filled your stack up and you'll get a stack overflow. So anyway, let's have a look how that works. So let's get rid of all this junk. I do apologise about the clicking. I can hear it on my speakers, it's so loud. Is this a new game from Zachtronics? I really like Zachtronic games, actually. What was the one I played? Oh god, I can't remember the name of it now. It was like six CPUs, and you had to pass information between them. It was really good. Yes, Richmond Mike, I do need a worse keyboard. I've got a nice fancy mechanical keyboard, but it's absolutely shite for working with. Yeah, TIS 100. That's the one. I absolutely love that game. It's brilliant. Yes, I do need a shitty rubber cap keyboard, to be honest. This is a gaming keyboard. It's really not suitable for programming. Well, not programming on stream anyway. I've just realised I've still got the music playing. I don't know if you guys can hear that. I just spotted it on my OBS. Whatever. It's not bothered anybody yet, so it's fine. Okay, so let's have a look. So we're going to jump to this subroutine, which is going to increment the border color and then return, which is going to bring us to here. So we'll put a jump to entry. And so this is just going to keep looping this section of code, and this section of code is going to keep running this subroutine. And so this should do exactly the same thing as we saw before with the border incrementing in color constantly. Actually, it looks slightly different. There's a reason for that, and that is because the amount of time it takes to actually run these functions. So if I was to put this in here, this is getting a little bit more advanced, but I think it's handy for you guys to know. So I'm just going to comment out that jump and do this increment instead. So if I do it without the subroutine, you'll see the colors look like that. Whereas if I do it with the subroutine, the colors look like that. Now the reason for that is down to cycles. So you've probably heard the phrase cycle exact or cycle stable timing, things like that. And that is basically how long it takes for these instructions to run. Every instruction that's run takes a minimum of 2 cycles from the processor. If you go back to the opcode site that I posted before, it actually, you see these numbers here? Under each of the instructions, that tells you how many cycles they're using. So if we look up ink in here, we can see, I'll explain again, there's more stuff in here, but basically this ink is an absolute ink, which is 6. So this is taking 6 cycles. I think jump to subroutine is 6 as well. Let me just double check, it might be 4 actually. No, it's 6, and jump I think is 6 as well. Oh no, it's 3. Okay, shows how much I know. So that's 6, and RTS I believe is 2. Oh no, RTS is 6 as well. Wow, this is why I don't like using subroutines. So what this is doing, so without this line, every time it runs this loop, it takes 9 cycles. One for this and one for this. That means the border color updates every 9 cycles. However, if we use this method, what we instead get is 6 cycles, plus 6 cycles, plus 6 cycles, plus 3 cycles, 21 cycles. So using a subroutine like this will take 21 cycles, and using it without the subroutine will take 9 cycles. And that means that the colours look slightly different. The reason for that is because every line on the VIC, assuming you use a PAL, right, actually let's show this in the debugger, it's probably easier to see it in the debugger. So Shift F7. Okay, let's go into that mode. Now there's a handy little tool in the debugger. Just going to put a breakpoint in here somewhere, preferably on a line that's actually getting run. Let's put the breakpoint on the increment. There's a handy little tool that lets you see where the raster line is, and the raster line is, you can think of it as the, well, it is the dot that updates your TV screen. So you know how a TV works, that it updates 50 times a second for PAL, 60 times a second for NTSC, and it's basically a single dot traveling from the top left of your screen to the bottom right of your screen 50 times a second, updating the colours of every pixel on the screen. If you press Control E, you can see in the debugger where that is. Now you can probably not see that. Let me skip it forward a little bit. There we go. You see that crosshair? That shows where the raster is at this breakpoint. And you can see that's where the colours begin and end. And that's because at this point, the colour is one thing, the command runs, and when it's run again, it's here. And when it's run again, it's here. And you see the colours update as it goes down. And you see how far apart they are? That's how many cycles it's taken between them. So you can see this gap here, it's like what, probably about half a screen. No, just less than half a screen. Now if we do the same thing without the jump to subroutine and just do the increment there, you'll see that that raster line happens much quicker. Oh, wrong one. I'm going to do that in the debugger. Yeah, hey, seriously, this debugger is the best thing ever. If you want to learn how effects work, this is the way to do it. Load a game up into here, load a demo up into here, and have a look how it works. So again, Control F8 to bring up the view here. I think you can do it in Control F1 as well. Let's have a look. No, you can't. All right. So again, we can see the cursor here. If if we press F10 to skip it through, and you can see now how the lines are much closer together, and that's because it's taking way less cycles for it to run the code. Now you can see it updating, so you can really see how these things change, and by timing things exactly, you can do cool stuff. So the Vic takes exactly 63 cycles to go from the left side of the screen to the right side of the screen on a PAL machine. On an NTSC machine, annoyingly, it's 64, so you have to do a little bit of extra stuff if you're doing some cycle exact stuff. But generally, if you just start working with PAL machines, just imagine it's 63. There's also the concept of a bad line, which I'll go into a bit more detail later on. But for now, let's just assume that lines take 63 cycles to complete. It's probably a bit more than you need to know right now anyway. Okay, cool. So how long have we been going now? I'm gonna take a short break to drink a little bit of wine, have a cigarette, and then we'll go into something a little bit more detailed. So the screen I'm going to put up next is the Be Right Back screen. It's also one I did this afternoon. It uses pretty much the same code as the starting soon code. And we'll load up the code that runs that, and we'll walk through it, and I'll explain how it all works and how you can do the same thing. So let's take 5, guys, and I'll be back in a minute. Right, I'm back, guys. That was a nice cigarette. It's raining outside as well, which is very weird. It's been very warm today. Okay, so like I said, we're gonna step it up a little bit now. I don't expect you to know everything that's in this code, but I'll try and go through it step by step so we can work out what's going on here. Again, if anybody, I'll reiterate what I said before. If anybody wants any help setting up Sublime with Kickassembler to launch C64 Debugger, or to launch Vice for that matter, please feel free to drop me a DM or a message on Discord, and I'll do my best to help you and get you set up as well. Yes, Mike, I'm going to put the code onto GitHub. I think I've yet to set the GitHub up, but I will include this entire repo on the this entire folder on GitHub as a kind of progressive thing as we go along. Feel free to kind of download it, play around with it, and do what you want with it. It includes a few libraries as well. Actually, I don't need that. I'm going to delete that. I'm going to delete anything that's unneeded and just leave the stuff that is needed. Yeah. Okay. Let me refresh the folders. Okay. Cool. Right. So this is the code I wrote today. Very, very simple code that does this. Why is that not working? Can't open file breakpoints. Oh, it's because I've just deleted that file. That's why I don't need that now. Okay. And you can see that's doing the starting soon logo. And if I change this to map 2, actually I've not got the colors in for this, but you can see I can change the text by changing the location. Be right back. I had a different color set for the be right back, but I'll explain that in a minute. So how did I go about making this? Okay, so the first thing I did, I took a font that I already had, which I've actually shared in my let's see, what's the folder? I think it's called Assets and Resources. Links, Asset Share. So if you go into Asset Share and have a look at the back through the history, you'll see files that people have shared. I'd invite everybody to share anything you want to share with the community, anything you want to be part of the game, anything you want to kind of share for others to play around with. This is the place to do it. Put your assets in there. There's another one called Code Snippets, where if you've got a nice piece of code that you think might be useful to people, put it in there. I would say try and keep it to Kickassembler just to not confuse people too much. If you want help converting it from another assembler to Kickassembler, if you send me a message, I can help you do that as well. But we're going to try and keep this to Kickassembler, as that's what we're going to use throughout this. But I've put the font that's used in this demo. Well, it's not really a demo in this screen. Into that links them into the asset share room in my Discord. I shall show you that now. So this is what it looks like. So I created this font. Okay. Yeah. So I created this font. I originally created it for Doc and decided I wasn't going to use it. I went for a 1x2 font instead of a 2x2 font. So I thought I'd drop it in the room and it'd be useful for people. But basically this is all the letters from A to Z. the numbers from 0 to 9, and I added an exclamation mark in for this for this kind of be right back screen, this exclamation mark here. Did I fill the font with empties? Yeah, so if you see from character 141 onwards, they're just empty characters. So I made this font. Feel free to use it however you want, and then I used it to build a small map. So if you turn tiles off, so have tiles disabled down here, you can just drop the characters in one by one, and create letters. So I created a small piece of text, 40 wide, too high. 40 because that's the width of this C64 screen, too high because that's the height of the font. And then from there you can go to export, raw binary file, export character set, and you can export the chars, which I did. I won't do it again just in case there's something different. And then, which is this bit here, and then I exported the map, which is this bit here, using the same method: import raw binary, import export raw binary file, export map. This is what happens when I drink wine. I can't talk. I can code, but I can't talk. So it's going to get interesting in another hour or two. What software is this? No, this is Charpad. So this is Windows software. Unfortunately, there isn't there's not one I find decent enough for me to use in Mac OS X. I'll show you what I did actually quickly. So I wrote an application using hacks. I don't know if anybody's used hacks before, and this allows me to. Hopefully, this doesn't load. Stuff I haven't shown. No, I don't think it will. Stop drinking wine and start drinking Vice. Oh no, I've got another bottle. I've got what? Another glass or two in here, and I've got another bottle in the fridge. So I fully intend on getting through that bottle before this stream is over. Yeah. So what Hacks allows me to do is create something that's cross-platform. My reasons for using Hacks is I used Hacks as a development tool at work. It was just easy for me to pick up. I don't think this Hacks UI is very good. It's the only kind of decent UI system out there for Hacks, but it was enough for me to be able to do this. And this allows me to kind of create fonts in here as well, so I can draw a font and a map, and I can see it update in real time, and I can draw a tile in real time. So if you know other languages, I would advise you to write tools that are suitable for your development, for your game development. Charpad and SpritePad are great, and they will let you do a lot, but there's limitations to them. For instance, if I'm drawing a tile in Charpad, I can't draw on the entire tile without compressing the char set. There's all sorts of reasons not to use it, and I do find writing my own tools is much more useful. For instance, another thing I can do in here, let me just load one of my maps in. You get a sneak peek at Doc in the making here now. It takes a while to boot up. I haven't actually got a compiled version. I just keep running it from. I use VS Code for Hacks, and I don't use Sublime. So I have a few extra buttons in here that don't exist in Charpad. Some of them do. I mean, you have this thing called materials that allows you to assign extra values to things, and that's kind of what I've got going on down here. Except I have more. I can do more in here than I can in Charpad. Let me load a map in. So this is Doc's, one of the current Doc maps. It's the World 2, it's the Ancient Outpost. What this lets me do is it lets me drop enemies in as well. So you can see I've got this sprite list here. I do need to work on this. This is just the sprites exported. allows me to drop enemies in, and then when I export the map, I get all the enemy data as well. So it's pretty useful. I would definitely recommend looking into your own tools if you can. It's pretty handy to have them. So for instance, if I want to create a new tile, I just pick a character where I want it to start. I add those characters to the tile editor, pick a color to start drawing, and I can draw on the whole tile, and it edits all the characters down here, and then I can plonk that tile. Oops. Go into edit mode. I can plonk that tile around on the map, and then I can look at where the collisions are. So I can see here, green squares are solid collision. These purple ones are things that are active. Blue are pickups, and so on and so on. Red is death. So also lets me see animations in real time as well. So you can see this. This waterfall here is these characters, and if I turn the animations on, I can see the animations run. It's another nice feature that you don't get in Charpad, so it's a handy tool to have. It may be something I share at some point, but to be honest, it's so built around Doc that the things like the map size, the tile size, the format of the enemies is very Doc specific, and the export you get is going to be not that useful. But things like the char set and the tile set, if you're doing a 4x4 tile, could be of use to somebody, so maybe at some point I'll release it. Anyway, to go back to Charpad, so so after making the map and the char set in Charpad, I export it and I get two files. I get the, let me find the files, desktop, let's make a game. There's actually three in here. So this is the starting soon map, and this is the be right back map. And these are just binary files. If you open them up in a hex editor, they're not going to make much sense. They're just binary files. They represent the data. Anybody who's ever done, please, Sean will share his. Yes, yeah, maybe one day. It's, if you're doing a 4x4 tile map with char set, feel free to ask me and I will share it. I actually have to show off one little thing in it again as well. I'll share it with you personally. Just do me a favor, don't put it online either. Use it personally. It's not suitable for mass kind of use, but it might help some people with some things. So the other cool thing that this lets me do, and this is very specific to Doc, if I want to change between the two worlds, I can see the tile sets update and the world update in real time, which is very, very useful. When it comes to designing the levels, if I need to know, do I need a ladder here? Do I need to draw a new power terminal? I can see by switching very quickly what I need to do. And again, I can see here yellow means this is a climbable object, so it's climbable in that world, not in that world. Okay, so let's go back. IPHXPT. I don't know how to pronounce that. I'm just going to call it Fext. And yeah, Richmond Mike, actually, sorry, Hayes, the Suck editor, actually, I used that for my first games when I was younger. I used the Suck editor to edit char sets and to edit sprites, and then I used the action replay to save them out. So I could load them into my own games. It was a very long and drawn out process, because I also didn't have a disk drive. I did it all via tape as well, which was horrific. But it was better than my other option, which was getting a piece of graph paper and some coloured crayons and basically drawing everything on graph paper and then manually working out what the binary was for everything. And my first games were done exactly like that. I didn't even touch on multicolour because it was just too complicated to draw everything in multicolour and then work it out in binary, and it was just too long. So I just used to do everything in high res at first. Okay, so back to this again. So we've now got two files. We've got this map file, which is 80 bytes long, each one of these being a byte, which references something in this char set. So for instance, this, the ninth byte, sorry, in the list references this in the char set, the top left corner of the B, and so on and so on. Thank you for the follow. Actually, thank you for the follow scope, Ivan, as well. I missed that one. Thank you very much. So, to go back to this program. So, you can see here, this is where the map is being loaded in. Again, we've got a label. Actually, let's go through it from the beginning. So, dot label. So, dot label is synonymous with kind of defining a constant in ES6 in JavaScript, or a constant in C. It's a way of assigning a number or otherwise to a name. And so there's two constants I want to create. One is screen RAM and one is color RAM. Now, I don't know how familiar you guys are with the Commodore 64, but the way that the screen works is you have screen RAM and color RAM. Screen RAM defines what is where, and color RAM defines what color the things are that are there. It probably makes more sense if I load something up in the debugger. So let me try. Actually, no. Let me do it directly in Vice, I guess. Hi, his Leo. Thank you for the follow. Okay, so let's load up Vice. Let's reset without that going on. Okay, so screen RAM normally starts at 0400. Now 0400 is in hexadecimal is 1024 in decimal, and that's this top left corner here. And then the screen is 40 wide and 25 high, so there's 1000 bytes, 40 times 25 bytes. So the last screen address is 2023. And by poking a number into there, we can put a character there. So you can see I tried to put the number 1 into 2023, and the character A appeared here. Likewise, if I go from the beginning and I do 1, the character A appears in the top left corner instead of 1. So with that in mind, we know that the screen address is at 0400. So what about colors? So nothing in there is defining the colors. So now I can never remember the actual decimal version of this. Unfortunately, in BASIC you have to use decimal. So let's have a look. So D800 is the color RAM. 55295. That seems wrong. Why is that an odd number? Pretty sure that's not correct. I'm assuming it's 55296. Let me just double check through here. 55296, yeah, I thought so. Okay. So 55296 with a value, I change the color of that to white. And, you know, I can change the color of that to anything. And it's just that one cursor there. So if I did 55296 plus 40, which brings me on to the next row, plus 1, 2, 3, 4, 2. What do you think we should see? And what do you think is going to change colour, if anything? I'll use this opportunity to drink more wine and find my vape pen so I don't have to go for a cigarette. There it is. A star. Yeah, Andy's right. If I do that, hopefully the first star in the Commodore up here should turn red. If I actually click on it, yeah, there we go. And that's because screen RAM and color RAM are two separate areas of memory. Now, unfortunately with the Commodore, and this is one of my bugbears with the Commodore, and anybody who's ever written any kind of scroller will tell you the same, color RAM cannot be moved. color RAM is always going to be at D800. No matter what you do, it's always going to be at this address. And that causes a bit of a problem, because if we want to move things very fast, the traditional way to do that, even with modern 2D games, is to double buffer things. And what I mean by double buffer is you have the screen, and then you have another buffer. You have another screen that you can't see. And double buffering means that while you are looking at one on the screen, the CPU and the GPU is drawing stuff on the other screen, the hidden buffer, the back buffer, if you like, that you can't see. And then when that's finished drawing, you just switch them, and you just keep switching. It's called double buffering. You can do that somewhat with the C64, but unfortunately color RAM cannot be double buffered. So what you get is that you can very quickly switch between two screens, but you can't switch the colors between those two screens. So you have to spend some CPU time to move those colors around. And that's why full color scrollers are quite difficult to do, because they take a lot of CPU time in order to move those colors around the screen. You can do all the tricks you want with the screen RAM, but you can't do it with the color RAM. But for now, let's just assume that the screen RAM and color RAM is going to stay in these locations. These are the default locations. As I say, the color RAM can't be moved. The screen RAM, this is where it originally belongs. You can change this, and double buffering involves changing this every frame. So you may change this from 0400 to 0800 and alternate between the two each frame. So the first two lines of this just set up two constants, screen RAM and color RAM. I should have probably put these in capitals, just to, I mean, this is kind of standard for constants. In fact, I'm going to do that now, and when we get to those values, I will change it. In fact, I'm going to change them now before I forget. Screen RAM. This is just a personal preference. I mean, you can label things however you want, but in my day-to-day code, I've kind of got into the habit of writing constants in capital letters like this. So, thanks, Dumper. Thanks for watching. I hope it's been enlightening. Can the NES do that? So the NES is a funny one, because this is where the power of the NES is involved. The NES doesn't have a lot of memory, but what it can do is it can display bit planes. So you have multiple layers of color, and it can scroll them a whole screen in either direction. So you're able to kind of have quite colorful scrolling backgrounds, as you see in games like Mario and stuff. There's other limitations that are different for the NES that cause other problems. I don't know too much about it. It's probably more for Zork to talk about. But yes, I mean, the biggest limitation for the Commodore is the fact that we can't scroll the color RAM. So when you see games like Mayhem in Monsterland or Turrican, the amount of colors that we're seeing there is the result of some very, very clever coding. And actually, in the case of Mayhem, some trickery to do stuff that really shouldn't be possible. We may go over that at some point. It's called VSP trick. I think I briefly touched on it in a game stream a few days ago. It's a trick that allows you to scroll the color RAM as well, an entire screen in either direction. But it's a kind of advanced technique and relies on cycle exact timing, which is what we went over before, having been able to control exactly where the raster is, not just in the Y position on the screen, but in the X position as well. Okay, so let me just check that that's working now. I've changed those values. It looks like it is because it's compiling. Yes, okay, right. I changed that back to map 0, so there we go, right. So we've now got the screen RAM and color RAM defined. Now we can use these values anywhere in place of these. Instead of referencing these hexadecimal addresses, we can use screen RAM and color RAM as constants. These don't take any bytes at all. This is purely for the assembler. No bytes have been written at all at this point. This is the first line that adds the bytes, and as we could see in the other one, it's literally just it's the thing that writes the basic program, the 10 SYS and the address. It's the pointer to the entry of the program. It saves. You can write this a different way, so instead of doing this, you could do 0801 being the beginning of basic, as we talked about before, and then you can do, or you can either do basic upstart, which is similar but doesn't set up memory, and then you have to actually set up the memory. So you define a place where to go to, and then you write whatever code there. Or you'd have to give that a label as well, like that. There you go. I use basic upstart too because I don't see the need of having to write these addresses in. Once you've started using it, you know where it's going to be. You may as well start using basic upstart 2 from the start. For a 16 kilobyte game, I was going to remove basic from memory. Most likely yes, because even though the game is 16 kilobytes, it is going to take more than 16 kilobytes of memory. We're going to use compression. I will talk about that probably in a future stream. The build pipeline that we're going to write is going to take our compiled program, our PRG file, and it's going to compress it down into a small file, and it's going to attach a cartridge header to it, and it's that file that needs to be 16 kilobytes. As long as it fits on a 16 kilobyte cartridge, then it should be fine. I mean, we've got actually let's talk about basic before we go into this program. Let's talk a little bit about basic. So let's go back to the memory map. Let's go to the beginning of basic. So basic starts at 0801 and it runs up to 9FFF. So A000 is where basic actually starts. You can see here the basic ROM is loaded into this area. So the basic ROM is 8 kilobytes of ROM that is used for running all the basic programs. So most C64 games will turn this off so they can use the full 16K, the full 64K. Thank you for the follow. Don't call me late for dinner. That sounds like a name my ex-wife might have told me to pick. Yes, anyway, so basic fits into this area. So what's interesting about that, and this is something anybody who's ever used a Commodore 64 will know. We open up a calculator and put it into programmer mode just to make... Also, if you guys don't already know this, programmer mode on calculators is invaluable. You will use this a lot for converting numbers. And we put 9F... Oops, 9... Oh, I need to be in hex mode. There we go. 9FFF, which is this value here, minus 0801, and we get that. Sorry, A00, because that's the start of basic, minus the actual start of the basic program memory, and we get 97FF. If we put that in decimal, look at what number we get. Who recognizes that number? This is why when we run Vice, or run a Commodore, should I say, not Vice. It's so used to using Vice. We get 38911 basic bytes free. And that's because that's how much memory there is. That's how much memory you've got to write a basic program between 0801 and 9FFF. Thought that'd be an interesting fact to show you guys. But yeah, if you're writing a machine code program, you don't need basic, so you can actually turn basic off and you can use more memory. So there is memory from default without turning anything off. There's memory from 0800 to 9FFF. There is some memory from C00 to CFFF, which you will see sometimes people write programs for. And then the basic lives here. So that's basic, and this is IO, and by IO I mean Vic, SID, Coloram. They all live in those areas, and then there is E00 to FFF, which is kernel, which is everything else basically. Now you can turn almost all of this off. The only thing you can't turn off permanently is IO, because obviously you need to be able to draw things to the screen, but you can turn it off temporarily. What I tend to do is I tend to store sprites in here, because once you've stored them you can then turn it off. The Vic will always read RAM, it will never read ROM unless it's char ROM, but I'll get into that at some other point. Okay, so let's go back to this. So this upstart is for entry, which is here. But before we get to entry, we've got these 3 labels. And these 3 labels are data that we're going to use for the program. You can store these anywhere. I mean, I don't have to put these in here. I can put these down at the bottom somewhere. But I like to kind of declare the things I'm going to use just before they get used, unless there's a specific reason not to, which there is with char RAM, which I'll explain in a minute. So let's go through. Let's start at the bottom with these bytes. So we saw bytes in the first program, this program, which is a fully runnable program, as we saw. It's fully accessible, fully runnable machine code. Changes the border to black. These bytes, however, are a little bit different. So they're still bytes, they're still numbers from 0 to 255, but what these are colours, and they're called colour ramps. It's a term you'll hear a lot, and I've got a really nice PDF which I'm going to drop into the chat now. And what this PDF does is it shows you nice colour ramps, nice visual colour ramps. So if I wanted to fade from why can't I scroll out? Has it crashed on me? I know. I can't scroll it with the sidebar for some reason. Okay. So if I want to scroll from colour fade from white to black, this is a chain of colours I can use. I can use 0, 1, 0D, 0, and so on. And what I've done is I've taken one of the colour ramps from the bottom. I don't know why that's not working, that's really weird. I think it's Chrome's PDF rendering is a bit funny. I've taken one of these ramps here. I've taken the black out because the black it looks like the characters are flickering on and off, and I don't like it. And I think this one is, looking at this, is the bottom one. So I've taken this colour ramp, so it goes from white, yellow, grey, pink, and so on, up to blue here. Bring the colour ramps up again, and then goes backwards again. So from once it gets to blue, it goes to B4, C, A, F, 7, 1, B4, C, A, F, 7. So, and 1 is back at the beginning again. What that does, it creates a list of colours. If we run the program and pause it, you'll see those colours. So you can see these colours are the same as in this list. So what we're essentially doing is we're drawing these characters to the screen, then we're using the colour RAM to set these colours based on this list. And then every frame, we're just shifting the colours along one. I'll explain how that happens, and that's to do with the colour index. So the colour index is just a byte that we store. We set it to 0 to begin with, and we use that for determining where to start the list in the list of colours. And the other command, this is a new command that we've not seen yet, is .import. And .import will take a file and it will import it. If you put binary after it, it will import it as a binary stream. So if we were to look at this in memory, which in fact we can do, if we go to the debugger, actually I should probably do this in the debugger, it's a bit easier. we scroll to the very beginning, which is going to be, let's have a look. It's around about here. So these bytes here represent this map, the map that we saw in here. In fact, if we open that map up in HexEdit, if we look in a hex editor, and look at the map, we can see, I bet you guys can't see that, it's very small. We can see that the bytes match 83838383 all the way up to 46. Actually, I'm showing starting soon 838383 46 47. Slightly different numbers. I don't know why. It might be because I'm looking at the wrong one, but it's basically, that's what that is. It's the data from that file. So this is all data that doesn't get run. This is just data that's going to be loaded in by the import statement or manually inserted by the byte command. And so we get on to the first entry point. I've commented everything again, so when I'll commit this to a GitHub later on, and you guys can look through this. So the first command is a load accumulator. It's in immediate mode, which means we're just loading whatever number follows. And the number that follows is in binary, which is indicated by the percentage sign there. So what does this mean? So let's have a look at what D018 does. So let's have a look at our memory map. So we look at our memory map, search for D018, and we see it's a memory setup. So what this is doing is making sure that the characters and the screen point to the right area. Let's scroll right down to the bottom of this. You'll see I've got this. This is loading the character font in. So in here it's this bit here, this bit of data. And I'm loading it into this address. This star again means this is where the program starts. This is where the entry point is for this part of the program, and I'm importing the character data into there. So it's at 2000. Now there's a reason I put it in 2000 and not a lower address. I could have put it in 1000, but you wouldn't see it. And I'll explain why at another date, but just know that you should not put graphics data at 1000 because the VIC will not see it. I'll explain at a later date why that is when we go over in more detail about how the VIC works. So to go back to the memory map. Memory setup register, so bits 1 to 3. Now bits, when you look at them, 0, that's bit 0, that is bit 7, so it counts from this end to this end. So 1 to 3 is these, so that's bits 1 to 3, so let's have a look what that does. So looking down this list, 100, and you can see that sets the character memory to 2007 FF, which is where we've loaded the font in. So this is saying load that font in, basically make that font the active font. And then the other bytes are these ones here, which if we look at the memory map, bits 4 to 7 pointed to screen memory, and we've kept the default address for screen memory, which is 0400, so 0001, and 0400 is up here. So it sounds like a complicated instruction, but it's actually not that bad. If you use a memory map and if you write the code using binary notation, it's actually quite easy to do. So again, I'll include this. You can play around with this. You can move the character sets into different places. You can try changing this screen RAM to different places and updating this to match. You'll see what happens. Next two lines, straightforward. We've seen exactly what they do. We load the accumulator with 0. We store those into the background and the border, or in this, the border and the background in that order. And then we've got a jump subroutine. So again, like I say, this is jump into a location, but with a view to return into here when it sees an RTS command. Before it does that, it loads the accumulator with 131. So let's go and have a look what this does. Now, when you're in Sublime, if you press Ctrl R, you can bring up a list of all the labels that are in there. So we're looking for clear screen. There we go. So there's clear screen. Now we've got two new commands in here that we've not seen. We've got store accumulator, $x, and we've got branch if not equal. We've also got a new label type, which I'll explain in a minute when we get to it. Let's start with the store accumulator, $x. So without the $x, this would take the value, which was 131, the one we passed in, the one we set before we jumped, 131, which, let me explain why it's 131. I believe it's that character there. It's an empty character. You can see it's nothing. It's blank space. So that's why we're passing it. We want to clear the screen, so we want to fill the screen with that character. Just jump to that again. So without that, the $x, what this will do, this will store that blank space in the top left corner of the screen. But that's no good. We want to store it over the whole screen. The screen is made up of 1,000 characters. So what we do is we make a loop. 250 times we're going to draw the character, the empty character, to the screen in 4 locations. We're going to draw in the top left, then 250 characters more, 500 characters more, 750 characters more. And then we're going to decrease the X value, and we're going to keep doing that. So actually it's not the top left because this is 250. So right, I should probably run this in the debugger so you can see what's going on. This is called indexed addressing. So what this does is instead of using screen RAM directly, what it does is it takes this address, which in our case is 0400, and then it adds the value of the X, which in our case is 250. Actually it's 249 because we've decreased X first. I'll explain why we decrease X first in a minute. So in the debugger that looks like this. I won't run because it's got a bug in it. Okay. Let's find that. Put a breakpoint in. There we go. Right. I need to rerun that. Perhaps if I look at it in this mode, I can't read it in the other mode. 2157. Okay, so I refresh. Oh no, not 2157 because yeah, it should be that. Why is that not working? Oh, it is. There we go. Oh, it's hard to actually tell in this. Okay, I'll explain what's going on in a different way. So if you imagine the screen, let's get this, let's clear this, and let's ignore the fact that it's that character. Let's imagine that's a blank character. In fact, let's go and blank that character. See away. Where's the char set gone? Okay, so this is our screen. It's 40 characters wide by 25 high. And now I'm going to fill it with another character. Doesn't really matter where, let's just do it like that. But in order to blank this screen, we need to fill it with a blank space. So the way we do that is we can use numbers from, what is it doing? Oh, okay, yeah. We can use numbers from 0 to 255, and the screen is 1,000 characters long. So if we blank out 250 characters at a time in a kind of row, and do that in 4 locations across the screen. So like this, for instance. I can't remember the exact locations, let's just imagine it's that. And then the next line we do that, and so on, until we've done 250. The entire screen will be blank. Now, the reason we go backwards, in fact, yes, let's talk about going backwards. Okay, so the reason we go backwards is because it's quicker for us to check that something is 0 than to check that something is 250. And the reason for that is this instruction. So if you have a value and you load it, you increment it, or you decrement it, if ever it reaches 0, this flag is set in the processor. It's called the 0 flag. You can see it here. It's where this Z is in the debugger. It's currently at 0, but it's running so fast you probably can't see it flicking. When that 0 flag gets set, then the last value it interacted with is 0. And what this branch instruction does is it says if the last value you decreased, increased, or loaded is 0, or that you did any operation on is 0, then branch. Otherwise, skip past this. And so this will keep decreasing the value from 250 until it reaches 0. And so what this means is these will actually be doing this. The first time round, it will be storing the accumulator here, 499, 749, 999, because we've decreased it here. I need some more wine. And then it says, okay, what was the last thing you acted on? This is the last thing. Stores don't affect the 0 flag at all. It's only loads, decrease, increase, and logical operators, which we'll get to another point. But you can assume that these stores will never affect the 0 flag, but this will. So this will decrease. If x hits 0, what will happen? So when x hits 0, this will now be. Let's put it back to what it was. It will be storing it in these values, and we'll have covered 250 characters in 4 blocks. This will say, are we 0? If we're not 0, jump back to here. But we are 0, so we'll exit. I realise I really struggle to describe incremented variables. So if anybody has any questions about that, please feel free to ask, and I'll do my best to answer them. It's not the easiest thing to explain. I'm trying to do it in a way that's kind of generic for people that do not know any assembly language. So if any questions, please ask. What's the significance of them? Okay, yeah, so when you create a label, if you wrap these braces around code that's within those labels, that code, then you can create labels that are unique to it. It's called scoping. You can create a label that's unique to this area. So let's just go to a blank bit down here. Say I have a piece of code with a label called A, and in here I decide I want to create a label called loop, and I want to increment the border and then jump to the loop. If I was to then create another label, it allows me to reuse that label. It allows me to reuse this name loop because it's unique to this. It belongs within these brackets. It belongs to this label. It's within the scope of B. So this you would refer to this as B.loop and A.loop. Without those brackets, if you were to do this, this would fail. And in fact, I can probably show you that just by running to make sure. Yeah, if I try and run that, I'll get an error down here, and that error will be complaining that the label already exists or something. The symbol loop is already defined. So this is a way of kind of sandboxing your code, basically. So you can reuse names over and over. And yes, so the exclamation mark is a special type of label. So this is I guess you would call it a relative label. So this lets you reuse things with it. So let me do one down here. So say I've got a label called A, and in here I've got loop, and I do the same again, but I want to create another loop in here. Again, that will fail because both of these loops are within the same scope. So because they're within the same scope, this will fail. Yeah, I will answer that in a minute, Acmafin and Vex. Yeah, yeah, they are going to be fun to try and explain. Yeah, so if I have two loops within the same label, they're going to fail, and that's going to fail because again we're going to get the same problem down here. What the exclamation mark lets you do is it lets you reuse a label, and instead when you do a jump, you say whether it's the first one back or the first one forward. Oops, sorry, they should be back. So you use the label, but you say use the last one or the next one. Last one, next one. And it also has a unique thing in that you don't actually have to give it a name. So one thing you will do quite a lot is loops like this. And when you do a loop like this, you don't want to have to keep writing loop in here, or loop 1, loop 2, loop 3 or whatever. So if you just do that, just do an exclamation mark and a colon, you can then refer to it as the last label, the last blank label. I'll use that quite a lot as we go on. You'll see that a lot. I think that's a Kickassembler thing. I don't believe that's used in other languages. There probably is something similar, but I think that notation is only used in Kickassembler. Okay, let's go through some of their comments. I think the exclamation is just a name, but yes, yeah, hey. So as I say, the negative and the positive symbol tells the assembler to look behind or in front for the next layer, for the next label. Acmafin, wait until you get into the address X and address Y addressing modes. Yeah, so there's a special mode of this indexed addressing called indirect indexed addressing that uses a 0 page. It's fairly complex to understand the first time. Once you get it, it's great and it's incredibly useful. But the first time you use it, it can be complicated. But we will get to that at some point. And I'm probably going to time it so I've not had quite so much wine when I have to explain that. I am going to top up though. Also, I think I'm out. I'm out of wine. I need to go and get another bottle soon. XPT, sorry I wasn't watching from the start. What compiler and linker to use? So this is Mad Nielsen's Kickassembler. I don't use any other linking tools. It's all just done with Kickassembler, and the preferences scripts in there. I use Charpad and SpritePad for importing binaries for characters and sprites. Some custom tools for my own games. Yeah, and the C64 debugger, which is very useful. Oh, thanks for the host, Caspian. Can you add Pinkhammer? Can you add another layer of brackets, or does the assembler assume you can? No, you can add as many as you want, so you can create more inside here. So going back to here, let's create another. If I create a label here, and I put a loop in here. I can create another level in there as well. And the great thing is you can refer to these differently as well. So if I call these loop 1 and loop 2, for instance, and I put I can do things like this. I can go jump loop 2, and then from here I can go jump a dot loop 1. So the reason why I can say loop 2 here is because loop 2 is in the same scope. It's at the same level, if you like. I use indentation. I think most people do in programming languages. If you're familiar with Python, you're absolutely familiar with indentation to define kind of block scope. So if it's in the same block scope, you can jump to it directly. If it's not in the same block scope, you have to use the kind of global label and then use dot notation to get to it. So in order to get back to loop 1, I have to say loop 1 that belongs to this block. Yeah. Okay, I never used indirect addressing, but no, when I understand it, I will. Yes, it's incredibly powerful. So I'll try to think of some examples that I use indirect addressing for. Collision lookup. So it's very useful to be able to store a kind of address in screen RAM. So say I know a character is, let me go back to Charpad. Say I know a character is in this location here. I can store the top left corner of where it is, and then I can use indirect addressing later on to get all the area around it without having to do some weird kind of self-modifying code. It's another way of doing. Python is a conspiracy to force feed you the uses of indentation. Indentation is good. I just hate languages that force you to use it. I think that's kind of bad. I'm not a massive fan of Python. I can use it if I have to, but I'd rather not. Anyway, yeah, indirect addressing. We will get to that at some point, where we'll have to basically when we do collision. I think that's when it will come in the most handy. Okay, I'm going to take a short break, and then we'll go through the rest of this program and explain how it works. For now, I'm going to drink some more wine. I'm going to get a fresh bottle, and I'm going to go and have a cigarette. In the meantime, enjoy the Be Right Back screen. See you later. Okay, I'm back. Got a nice fresh bottle of wine as well. Got one more glass to go and I can start on a fresh bottle. Let's catch up with the chat a little bit. Yeah, I hate Python. I really do. Python and Ruby, both of them. I've had to use them both before, and I'd rather not use them. I'm actually fighting at work at the moment to get a lot of the scripts we use on some of the build servers changed from Python, because it's just not easy to maintain, especially when you haven't written them yourself. Yeah, exactly. Not hunting bugs, you're hunting indentation. And it's so simple to cause problems with it as well. Started to learn C in the 90s. Is C still a thing? Yeah. I mean, it's really useful to know a little bit of C and a little bit of x86 as well, even when you're doing JavaScript stuff, because it's useful to know exactly how the browsers compile your code down into x86, and in order to do that you need to be able to read C to see how the V8 compiler works, and x86 to understand how it's trying to optimize certain things. But it's definitely worth knowing a bit, even though I don't use it very often. It's handy to know. It definitely helps out now and again. You start that Patreon. Honestly, I don't know enough about Patreon. If anybody's willing to tell me what I should do with it, I don't know exactly how it works. It's kind of like subscriber content, I think, isn't it? I have considered kind of putting all this into some kind of not a book, but in some kind of documentation so people can read it as well, because videos aren't always the easiest thing, especially a stream like this where there's a lot of kind of interjection and stuff. Way to learn 6502 is to make your own coding is kind of just seeing, you know, all the modules, they're all based on C. Yeah, in fact there's even compilers for 6502 that will compile C into 6502. There's targets for C that will do that. There's a really good video from one of the conferences a few years ago of a guy making, I think it was like a breakout clone in C that ran on the C64. Create a page, put your YouTube from this channel, update every week, watch the dollars roll in. Yeah. Yeah, I don't know how much use this is going to be to people. I'm going to keep doing it. I really want to make a game with the community, and I'm hoping that by doing it as part of the community that we'll get more and more people involved in the scene. I think the Commodore scene is incredibly burgeoning at the moment. There's so many people coming into it, and it's growing so much, and I think if people can get into it easily, there'll be even more. I love the system, I love the architecture. Yeah, I mean, okay, maybe it's something I'll look into this week. I may badger people for a bit of assistance with that. I'm fairly new to all this. Twitch is still a little confusing to me, but I'm getting the hang of it slowly. Okay, so let's go back to this program. Okay, so the clear the screen function is basically just filling the screen RAM with the character that we send to it, and it's using this loop to do so. Actually, before we continue on, let's talk about the process, the processor CPU flags. So if we look in the debugger, then we can see a few. So I'm gonna put this on this screen so I can copy it down here. I'm just going to write the flags in here. So the flags are NV VDIZC. So these are the flags that are available. A flag is basically just a single bit on the processor register that allows us to check various things. I'm not going to go through them all now, but I'm going to explain. Let's see. I'll explain two of them now, and we'll explain a third shortly after that. The others you probably won't use very much. Goes down here. Yes, there is an annoying missing flag in the middle. I've always wondered if there's a way to say. Anyway, let's not go into that. The two that we'll look at now are the negative flag and the zero flag. No problem, Mike. Yep, I'll be going until I finish this bottle, most likely. So the stream will be on Twitch straight after this immediately, and I'll do a slightly edited version to take out the be right backs and the started scene to put onto YouTube. Yeah, thank you for joining. I hope it was of use to you. So the two flags we're going to talk about are the negative flag and the zero flag. What do they do? So if we take a value and we put it into the accumulator, or any register, we can put it into the accumulator, we can put it into X. It doesn't really matter. If we load a value into one of the registers, then one of these flags, both these flags are set depending on what's in there. So the negative flag is set when well, let's do the zero flag first. So the zero flag is set when this value is 0. So if we imagine these bits in memory are 0, 0 to begin with, and we load 1 into it, then the zero flag is not set because this isn't 0. However, if we were to put 0 in there, then the zero flag would become 1. And the zero flag is important because that's what this instruction does. There's two instructions that use the zero flag. There's branch if not equal and branch if equal. And what they do is they branch the code, they change the program counter to point to a new location if the condition is met. The condition here is that it's not 0. The zero flag is set to, the zero flag is off, and equal is if the zero flag is set. So in the example we've got here with this loop, X starts at 250, and every iteration of this loop it gets decreased by 1 until it hits 0. When it hits 0, this condition is no longer true, so the jump isn't made to here, and we exit the subroutine. So that's the zero flag. The negative flag is a little bit different. So numbers go from 0 to FF, or in binary, let's put they're 8-bit numbers, so 0 to 255. Let's put all the numbers in here. So 0 to 255, 0 to FF, or in binary, that is 0, 4, 4, 2. Interestingly, you don't have to put leading zeros in, so that's perfectly valid. That's perfectly valid as well. Same as you would do with normal numbers. Nobody writes 0 as that. Everybody writes as that. It's exactly the same with these other numbers. It's just easier, I think, especially with binary, to put all the numbers in because it makes it a bit easier to understand. So what is negative? So obviously 0 to 250 is all positive numbers. And so the way that the 6502 and most other languages deal with signed numbers is by using the bit 7. That. So this is now saying 128 to 255. Those are negative numbers. Now, it's hard to understand when you think of it like that. So the way I like to think of it is you imagine a number line. So you've got a number, and it's got 128 in the middle, and you've got 255 at the end. In order to create a negative number, what the Vic does is it splits it. So once it gets to 127, that part of the number line goes here. Everything this side of 0 is positive. Everything this side is negative. I can't draw it, there we go. Everything this side is negative. So 255 is -1 because it's 1 away from the 0. All the way down to 128, which is minus 128. I think if you think of it as a number line, it's a bit easier to understand. And the branch instructions for that are branch if minus, so if the negative flag is set, and branch if plus, if the negative flag is not set. So what that means is if we load, let's load a binary in to make it make sense. If I do that, then the negative flag is going to be set, which means this branch will not happen, because this is only going to branch if the negative flag is not set. However, if I use branching minus, it will jump, and I've missed a 0 off there. Because bit 7 is set, this number actually represents minus 128. I'll explain the importance of that later. In fact, no, I'll tell you what, I'll show you a different way to do this loop. I need my leading zeros, I get very OCD. Yeah, I'm the same, especially with the binary. I think if I cannot stand when I see binary written like that, and then, you know, it's difficult to read. I have to then kind of think in my head, all right, that's that, you know. It's much easier if somebody just fills in the pissing leading zeros. It's much easier. Sorry, I'm getting angry about leading zeros now. Okay, so let's have a look how we could do this loop using the negative flag instead of the... oh, in fact, no, we can't use the negative flag here, and the reason being is because this is already a negative number. So if I was to change this to that, it would immediately exit, because once it gets to here, the number is 249. 249 has bit 7 set, and so it will exit, and this is why we use not equal to 0. Okay, so that's the negative and the 0 flag. There's another flag that we'll use quite a lot called the carry flag. We'll go through that when we get into addition and subtraction and comparisons. For now, you don't really need to understand it. I'll just check if we're using it in here. I don't think it's being used in here. No, I deliberately wrote it so it wasn't. Okay, so let's go back. So to reiterate, code, the assembler creates a basic line which points to this entry point. Before the entry point we have some data, which is the map, the color ramp taken from that documentation, and an index counter which we'll use later on. We also have the character set which has to be imported at this location. If we try to do this up here, it would still work because we've now set the kind of internal assembler counter to 2000. So this binary would get imported, but this code would now start at, what would it be? It would start at 2800. And that means there's a massive gap between here, between here and here. It's just neater to import these in a different place. What I actually like to do is with things like this, if they're imported in a different location, is I'll have another file. I'll import a file which will then import those before all of this. So I'll show the imports demo another day. It doesn't really matter, but yeah, we can move things into other files if it becomes difficult to understand. So once the basic program jumps to the entry point, it sets the memory registers to point to the new screen RAM and the new character RAM, as we looked at in the memory map. Again, if you need to know where that is, just jump into the memory map, look for D01A. If you forget what it's called, you can just, if you do go to this page and you search for character memory, it will take you and you'll see it's D01A, and then you can work out which bits you need. Just remember, this is bit 0, this is bit 7. This one isn't used, so you still have to put it on the end. It can be 1, it can be 0, it really doesn't matter which one it is, as long as you have it there. Otherwise this becomes bit 0 and not bit 1. So once we set the char set, we set the border to black, we set the background to black, and we clear the screen by filling it with this number 131. So the next step is to draw the text. Now we loaded the text in here. So we have a label which points to a place in memory which has the mapping. The map is, let me load it in. Oh, what have I done? Have I not saved it? Desktop, let's make a game. That's it. No, desktop. So there we go. It's this. So it's these 80 bytes here. You imagine taking the screen. If we were to put these 80 bytes in the middle of the screen, we would have starting soon written across the middle. And that's exactly what this next function does. So we could have made another function for this, but I haven't. I've just done it in here. This could have also been, and we could have made a method, a subroutine, if you like, somewhere else, and put this code in with an RTS on the end. But as I showed before, doing a jump to subroutine and an RTS takes 12 cycles. So it's probably good practice to get used to writing small things like this in line in the middle of the code, rather than creating subroutines for absolutely everything. Clear screen is a good one to create a subroutine for, because you will do it more than once. You will do it a lot. So because you will do it a lot, it makes sense to separate it out, so you can just call it like this all the time. Later on, when we get into more of the Kickassembler stuff, I'll show you how to make macros and how to make functions that can do similar things as well for reusable code, if you want to write very small snippets of code that you want to reuse without using jump to subroutine. Negative numbers are just interpretation when the high speed is set. If you interpret numbers signed, it's negative to you. Yeah, exactly. It doesn't have to be negative. I mean, the way to think about it is it's always a positive number. Okay, so if you take ff, if you take 03 and then you add ff to it, ff is a negative number, which is, it represents -1 as a negative number, and this represents 3. And if you were to add those two numbers together, this would loop over, like I said. Once it gets to 255, the next number is 0, and the end result would be 02. So adding these two together actually creates the result you would expect from adding 3 and -1. So that's why it's set up the way it is, and that's why it's handy to think about it as a number line. The number line kind of is what changed the way I thought about signed numbers. I couldn't really understand them properly until I thought about it like that. So it's worth kind of just trying out some, write it on a piece of paper, try out some additions, try out some subtractions, and you'll see that actually signed numbers are just numbers. It just happens that if you add numbers that carry over into the 9th bit, then actually you will end up with negative numbers automatically by adding 2 positive numbers that overflow, if you like. So this loop sets x to 0, and then we're using this index thing. So we get a character from the text map. So we get a character from, let's load this up and make it a bit smaller. Where's it gone? There it is. So x is 0, so we're currently getting that character there, and we put it in screen RAM at this location. So why 12 times 40? 12 times 40 is because we have 40 characters wide, and 12 is how many rows down I want to start drawing it at. I've just got something, I don't know what that is. Oh, music links. Thanks for the follow, music links. And again, we use x. So what that's doing is it's putting it in it's taking the first character and it's putting it in the first position of row 12 of the screen. And then it's incrementing the x. And then we get this command. So this is a compare command. Now what compare commands do is they take the value in a register and they compare it to another value. We're using immediate mode, so we're comparing it directly to the number 80. And what it will then do is it will check if it's equal to 0 or not. Now, when I say if it's equal to 0, the way to think about this is if I put the value 0 into x and then I compare it like this to 80. Let's do it in decimal as soon as it is in decimal. The reason it's 80, by the way, is because it's 2 rows of the screen. 2 rows of the screen, 40 wide, 80. And that's exactly what we've got here. 2 rows, 40. What it's actually doing is it's taking the value that you want to compare and it's subtracting the value in the register. And that equals 80. And so it's not equal to 0. A compare instruction will set the 0 flag if the value matches in the accumulator, because if I put 80 there, that now becomes 0 and the values match. Because the values match, the value is 0, and so the 0 flag is set. And so what this is doing, it's incrementing x until it reaches 80, and when it reaches 80 the 0 flag is set, so it no longer jumps back and repeats this code. So this code is repeated for all values from 0 to 79, and at that point it breaks out and continues from this point onwards. And that's exactly 2 rows of the screen. So what's happening is it's taking the first character here, putting the first character of the screen, incrementing x, jumping back to the LDA command, going on to the next character, index 1. You can actually see the index down here actually, x, and down here where it says ready now, when I hover over it, x is 1, x is 0. Everything starts at 0, not 1. Something most programmers are familiar with. Yeah, so increments x to 1, so now it takes the second character from the map, puts in the second character on row 12, and it continues to the end of the row. Then at the end of the row, the next memory address is the second row of the characters. It also means it's the second row, the 13th row in screen RAM, because we're using starting at the 12th row. And therefore it copies everything into RAM. So if I was to just put, I'll explain what that is in a minute. I was just to put that in there, you'll see it draws our characters on the screen. This is a useful way of just halting the program. What this is doing is when it gets to this line, star is equal to this address, the address of this thing. It's the equivalent of doing that. Because the label is the same as this address, you can just put star and it will do that. It only works if you want to jump to the same command, you want to jump to the same spot. You wouldn't use it any other place, but it's a good way of just halting execution if you ever need to do that. So, so that gives us the starting scene on the screen. There you go. So now with those on the screen, what we want to do is we want to colour them, and we want to colour them using this colour ramp that we've defined up here. So this is where it gets a little bit more complicated. We're still using the same methods, the same commands that we were using before, but now we're using a lot of them and we're doing a lot of comparisons and a lot of extra tricks. So let's go through it step by step. Actually, it might be worth me doing this. Yes, let's do this in the debugger, because you can probably see it in a bit more, because this is looped, so this is happening all the time. Okay. Should be easy for me to break into. So there's the label loop. You can see it's put the labels into here in this mode. If I put a break address in there we go. So program counter is now at this point, so we're now here. Color index is the byte that we declared up here. It's just 0, so it's just a memory address with 0 in. Let's find the right window. We can see that 086C, so if we look up here, 086C, it's probably not 0 anymore because it's run a few times, it's actually 05, but it doesn't matter. Anyway, Scroll back down to the code. So if we step through this, what's it doing? So it's, first of all, it's setting the X register with the value of this color index. I don't know if you can see that. Is that still clear? Yeah. Okay. So let's step through. So we can see it's set the X register to 5. That's the value that's currently in that location. Increments it. It's now 6. And now it compares it to 14. So why 14? Well, the reason it's 14 is because we've got 14 numbers in here. So this is 0, this is 13. So if X gets to 14, then we need to set it back to 0. And we do that by comparing it to 14. If it's not equal to 0, if the comparison is not 0, i.e. if 14 minus X not equal 0, sorry, that's that. 14 minus X isn't equal to 0, then we go here and we don't do anything else. If it is equal to 0, that means that the value has hit 14, and so we have to reset it back to 0 again. And that's so that when we get the colour, we go through the list of colours, and when we get to the end, we go back again. Simple as that. We're just looping through that list. So at this point, we've got a new colour index, and we can store that colour index for use in the next section. Now we need to put them colours on the screen. So we're going to set the Y register to 0. The reason we use the Y is because we're using the X to grab the colour, and we'll use the Y to grab the screen position. So we set the Y to 0, then we load the accumulator with a value from the colour ramp that's X position along. So we set that here. So that's going to be one of these colours along here, depending on where we're at. I think in this case we're actually at 6. So we grab this colour here, which I think is purple. And we store it in colour ramp. And you see again we're using 12th row, 12 times 40, 40 characters in a row, 12th row down, plus 8. Now the reason we use plus 8 is because if we look at here, 0, 1, 2, 3, 4, 5, 6, 7, 8. The first character we want to change the colour of is 8 characters long. So it's 8 characters in, and it's actually 24 characters wide. Yep, we could reverse the colours. In fact, we probably wouldn't even need to reverse the colours. We could just, in fact, when we've gone through this, I'm going to do that. It's a really good exercise to learn why decrementing is better than decreasing down to 0 is better than incrementing. We'll do that in a minute. I think that's probably a good idea. Yeah, so we've got the colour from the colour ramp. We set the colour on the screen. We start at 8 characters long. We set the first character, this one here, on each row. So the first column of the text to be the colour that we picked up, and then we increment the colour index. So we go to the next colour in the list, and we do the same check again. If we've got to the end, then we go back to the beginning. So we see here, increment the X. If it's 14, set it back to 0, otherwise jump past. And we also increment the screen column index. And then if the screen has got to column 24, we're at the end. So what that's doing is it's advancing through these columns and advancing through the colour ramps. So if we advance through this program, we should see that happening. So if you look at the S, you should see it start to change colour. So that's the first column, and now it's incrementing X to 7, incrementing Y to 1, and it will keep repeating that, and it will keep incrementing the colour. See, as we go along, it's incrementing, and as we get towards the end, as y approaches 24, which is 18 in hex, it stops, and at that point we go into the next step. The next step is, if anybody's got any questions, by the way, please feel free to ask, because I'm kind of rushing ahead a little bit here, and I'm conscious that some of this may be a little bit confusing to understand at first. Premature optimization. Actually, this is probably one of the few cases where assembly is probably one of the few cases where premature optimization is a good thing. You should get used to doing things in a certain way. I kind of have deliberately written this quickly and kind of simply. There's many things I could have done in here to make it much faster, but I deliberately haven't, because I've tried to reduce the concepts down. I didn't want to overwhelm people with too many concepts, which brings me on to this next bit. So this is not the best way of doing this, but it's the simplest way I could think of doing this without forcing you guys to learn about raster interrupts straight away. So what this is doing is ensuring that this code only updates once per frame. So we talked briefly about the raster before. You can see in the debugger there's raster Y and raster X. Now the only one you can really read is raster Y. I don't think there's a way of reading raster X. I think this debugger just has a way to do it, as far as I know, and please somebody correct me if I'm wrong. There is an easy way to read raster X. You'd have to calculate it yourself. So if we go into this mode and turn the raster on, you can see now we're at the bottom here. The raster's got to this point, it's drawn everything, and that's because we waited this chunk of code here, these 3 lines 69 to 72, they waited for the raster to get to A0 before they ran that code. The raster is now at AC. You see, if I go back to what's it? Oh God, I can never remember which button it is. If I go back to this mode, as I move it around, you can see the raster Y up here in the top corner increment, and it starts at 0, 0 at the top, which is in the border. It gets to 3, 2, I think, or so, which is the edge of the screen. 3, 0, 3, 2, yeah, and goes all the way down the screen. FA or so, yeah, FA. And then it goes off the bottom here. And when it gets to FF, it carries on, because this actually goes 312 lines on a PAL machine. There's less on an NTSC machine. I couldn't tell you offhand how many there are. I'm sure somebody in chat could tell us. But it's less on an NTSC machine. This is why you will see more games for PAL, or more optimized for PAL than NTSC, because there's just less time to do things on an NTSC machine. An NTSC machine runs at 60 Hz, whereas a PAL machine runs at 50. And they make up for that by having less lines on an NTSC screen, because it goes through the lines quicker. They still run at the same well, I say megahertz. Well, it is megahertz. It's 1 megahertz, isn't it? They run at the same speed, and therefore, in order to make 160 and 150, they had to reduce the number of lines on an NTSC machine, and the number of cycles is 1 more on an NTSC machine, so you get 64 rather than 63 cycles in a line. But you can see as we move up and down, you can see the raster counter here that says where it is. So I wanted to make sure that this updated as soon as the raster line had gone past. I would start updating the colours. The reason I do it when it goes past, because if I do it here, if I started updating the colours here, you would see them changing as the line went by. You would kind of get some glitching as it was kind of updating, trying to draw stuff that was currently being updated. So by doing it here, it's not going to update until this raster goes all the way down to the bottom, back up to the top and back down again. By then our code has run and changed the colours. When it goes past the second time, you see the colours update. I'm not sure actually. I do know that it runs at 60 Hz, and I know that the number of lines, the number of vertical raster points, the number of lines that it renders is less on an NTSC machine. If it is slightly faster, it's not by much. The reason why you will, if you get a power game and you run it on NTSC, the reason why it feels faster is not necessarily because the CPU is faster, but it's because they're running code every frame. And by running code every frame, if it's on a PAL machine, that means the code runs 50 times a second, whereas on an NTSC machine, it's going to run 60 times a second. So it's not, I don't think it's so much, yeah, see, Acmafin, yeah, it is slightly faster on the NTSC, but the reason why you feel so much of a difference with an NTSC game is not due to the clock speed, but it's due to the fact that it's running code every frame, probably using rastering tools. So the music will be like 17% faster because the music will be updated once a frame, which on a PAL machine is 50 times a second. On NTSC, that means 60 times a second, which means the music is going to update 17% more often than it should do. So what this bit of code is doing, we load the accumulator at A0, which in here is just below A3. Yeah, it's just below the text here. And then we compare it with this register. Now this is the first time we've seen, other than using the store accumulator, we've seen an instruction not use immediate mode. So this is a compare instruction again, but it's not comparing to the number D012, it's comparing to the value that's in D012. If we did that, it would be comparing, even though that's illegal because it's a 16-bit number. But if we did that, then it's an immediate mode, which means it's comparing the value in the accumulator to this value, to D0. By omitting the hash symbol and doing that, instead it's comparing it to the contents of D012. So again, let's have a look at the memory map. And it's a VIC register, so anything between D0 and D040 is a VIC register. And D012 is the current raster line. So what this is doing, it's saying, take this value, take the current raster line. So say the raster line is at C0. Take away the number we're comparing it to. Is it equal to 0? Well, it's not. And it will keep doing that until it is equal to 0. In other words, until it is that value. So this will loop until the contents of this memory address equal that value. Which means, if we look at the code, so this is the code here, loop is the breakpoint. This loop is the breakpoint we set back up here again, where the colours start incrementing and then the new colours get drawn. But let's go to this mode and turn on the raster, which you can see. And see this chunk of code here is that comparison that we had. Where is it? There. Debugger. So these three lines of code, load commit with A0 compared to D012, branch if not equal. I should probably explain at some point why these numbers look weird on the branch instructions, but for now, rest assured that that is correct. That same branch if not equal back to here, it's pointing to the same label, but the operand is not B208 like you would expect. It's FB, and it's because it's a relative jump, but we'll talk about that later. It's not important for now. You'll rarely have to worry about that. So let's skip through this code and watch the raster and what happens. So you can see the code is just hovering around here. It's not doing anything. It just keeps comparing to the accumulator. The accumulator is A0. The value in D012 is this value here, and it keeps going and it keeps going and it keeps going. And this is going to take forever, actually. I'm not gonna hold this down until it happens. But rest assured, what's going to happen is this is going to keep going and keep going. It's going to go all the way off the bottom of the screen, and it's going to come all the way back to the top of the screen, then back down until it hits this point here, which is A0. And when it hits A0, it will jump back to the loop and it will do the colours again. It will shift the colours across. So if I press F11, it will continue to the breakpoint, and you can see
The raster's at A0, and we're now at this point, which is here, and we're going to run the color code again. Let's start stepping through the code in Vic mode so you can actually see it. I can never remember which button is which for Vic mode. That's it. It's already gone past, so jump, there we go, you can see the colours updating. There they go. And you see how the raster is ahead of that, so what you're actually seeing on the screen at the top, so the screen at the bottom here is actually what's happening in the Vic. The screen in the top right corner is what you can see on the screen. And you see how the colours that you can see on the screen don't match these, and that's because the raster line hasn't got there yet. So if I press F11 to skip back to the breakpoint, you'll see the colours update and they now match. So that's a sneaky way of just holding the execution for a frame. You just tell it to wait for the raster to get to a certain point and just keep looping. It's not ideal because you can't do anything else during that time. That's a blocking loop. I'll introduce the concept of raster interrupts later on that allow you to create subroutines that are jumped to when the raster reaches a certain point. They're a slightly more advanced subject. I think when we start doing the game and we get to them, I'll explain those. But for now, this is a sneaky way of just holding on to the raster. What you can do, for instance, if I put a couple of those in, I put them 16 apart like that. Let's just do 3. And then I change the background color here. Let's do red. I'll copy that and change the background color here. Purple, and then black again here. What that will do is it will wait for the raster to get to A0, then it will change the background color, then it will wait for the raster to get to B0, which is 16 lines down, 2 characters down, and it will set the background to purple, and then it will wait for it to get to Z0, another 16 lines down, 2 characters, and set it to black. And the end result of that is we get raster splits like that. And that's how a lot of demo effects work. They will wait for raster lines to come to a certain point and change things. The reason we're getting flickering there is because these values might not actually be hit dead on. It may be that they go slightly over, and that's to do with bad lines. We can probably fix that by doing something like that. Just intrigued as to whether that works or not. But for now, that's a topic for another day. Bad lines. Good night, Dom. Nice to see you here, and you're very welcome. I've enjoyed doing it a lot. It's I just hope it's been of use to people. I will continue doing it. It's a lot of fun. Sleep well, mate. Yeah, so that's basically it for this function, this little demo. And so what this is doing is, let's quickly run through it. Creates a little basic program which jumps to our entry point here, imports some data, some from a file, some manually inputted, sets the character set and the screen RAM, sets the background and border to black and clears the screen, then draws our text, which we loaded in here, on the 12th row of the screen, covering 2 rows, 80 characters. and then it sets up a loop, and this loop increments the color index every frame, and then uses that to color the screen RAM in. And we get that. So as I said, I'll push this code onto the GitHub. It's probably, I might organize it a little bit better, because this is going to be the game folder. I just wanted a folder to start in, so I might make a tutorial folder. So I may adjust the code slightly to deal with the different folder structure, but it will essentially stay the same, and you can play around with this in Kickassembler. If anybody does have any questions about it, then please feel free to ask and message me on Discord or Twitter or anywhere, and I'll help to get you set up and get this running. Okay, so to the tools, ASM, etc. Yes, I'd say when I upload this to YouTube, which will be tomorrow morning, Fex, I will add the links into that YouTube. Oh, there you go. Hazes added it in there. But yeah, I'll add all these links in as well. Everything I've covered, every link that I've posted into chat, I will post them into the YouTube comment, the YouTube description as well. I think it's probably a good time to wrap this up. Actually, I thought I could go a bit longer. I've not even opened my bottle of wine, but I think it's probably a good point. We'll continue this next week. Next week we'll start actually making the game, so we'll look at what we need to do in order to display our map using similar code to this, and we'll come up with some new functions, new methods, some new libraries, and look at starting to build the game. So I'm going to do a couple more votes this week. I think we need to decide kind of top-down or side-on view, and maybe we'll look at some actual kind of design stuff. So what kind of character we're going to use. But I'll post those on my Twitter this week. Please join the Discord. Follow me on Twitter. Follow me on Twitch as well now, and join in the conversations. Next week will be a little bit more coding, a little less explanation. I will still explain everything as I go along. I think it's important that every single command you've not seen before you should know, and hopefully you guys have got something out of this. Yeah, that's it. I think I'm going to go and play some games. I may actually stream some, so why not? Right, thanks guys.